Good afternoon, everyone. Hope you're all well. It's Dr. Bennett here to take you through the last section of Chapter 6, which is on frames and machines. So frames and machines are another extension of trusses and truss structures, and I recommend that you go through section 6.5 in the textbook, which starts on page 282. But here in this video we're just going to go over some of the basic concepts and an example of each, both a frame and a machine example. So as I said, frames and machines are extensions basically of trusses. So in the past, when we've discussed a truss, for example this top one here, we assume that each member of the truss is a two-force member, which you will recall means that the members are only supported or loaded at the joints or the nodes of the truss, which means that each member is only subject to axial forces, whether that's tension or compression. A frame, on the other hand, for example this sketch down here, you will see that not all of the members are supported and loaded at the joints. So for example, we have this external force applied here in the middle of the member, and what that means is that not all of the members are two-force members, and that they may also have bending, shear, torsion forces in addition to the axial forces that we saw for the trusses. So the giveaway when identifying a frame and how it is different to a truss is that you will often see externally applied forces in the middle of members, and these offset sections of the frame which are not necessarily triangles, right? And then finally, a machine is basically a frame which is designed to move. And the textbook gives some examples of what a frame may look like. So for example, you may see examples of tools, of gym equipment, for example, like this example down here. There's like some construction equipment as well, like the diggers here and the tractors. So they're all examples of what machines may look like. So there is a slightly different solution method when dealing with frames and machines, and I've quickly sketched out a kind of basic structure to the solution method here. As always, we start with a free body diagram of the entire structure. Then we try to identify all two-force members so that we can eliminate them from our sub-free body diagrams. Then we disassemble the structure and draw a free body diagram of each of the members separately. And where any two members are in contact, we have to denote equal and opposite component forces in both X and Y directions. So you'll see an example of this in a second when we get onto the examples. And then the final two steps are what we've seen in the past, right? So for each of the sub-free body diagrams of the individual members, we can apply the equilibrium equations to each member and then solve a system of simultaneous equations to get the unknown forces. So we're going to have a look at an example of each, of both a frame and a machine right now. So today I'm on the Gatorade. Keeps me going in the afternoons. By the way, the green one is the best one, the apple one. but due to the hard times that we're under at the moment, I could only get my hands on some blue. So comment below what your favourite Gatorade flavour is. I like the apple one, or the lime and cucumber one is also a good one. So right, let's get on with this. So a frame example then. So this is example 1. We have 2 members, A, B and B, C. They're both supported by pin supports at A and at C. We have some dimensions. We have this externally applied force of 2000 newtons. So that's applied in the center of member BC. So that's the giveaway that it's a frame and not a truss, right? And the question here is to find the reactions at the pin supports of the frame. So we need to find the unknown reactions. Remember that for a 2D pin support, we will have a reaction force in both the X and Y at both A and C. And the question is to find what those unknown reactions are. So the first step, let me refer back to my solution method over here. The first step was to draw a free body diagram of the entire structure. So that's what I've done over here. You can see I've included the reaction forces at the pin support, so I now have an FAX and an FAY over here, and I have an FCX and FCY over here. And then I basically completed the free body diagram with a coordinate system. I have my angles, dimensions, I have the joints labeled as well. But the problem that I've run into here is because I have 2 pin supports in the original diagram, I now have 4 unknown reaction forces. So I'm actually left with a statically indeterminate system, right? Because I can only apply 3 equilibrium equations in 2 dimensions. So, continuing with my solution method, the next step is to identify all 2 force members. So I can acknowledge over here that although member BC has got an externally applied force in the middle of it, meaning that it's not a 2 force member, the member AB is only loaded and supported from either side at the joints, right? So member AB is actually a 2 force member, as I've written here. So that's going to make math a lot easier when we are able to reduce the components of the reaction forces at A into one axial force in this direction at an angle of 60 degrees from both sides, right? So that's step 2. Step 3, if I refer back to my solution method, is to disassemble the structure and draw a free body diagram of each member. So, separating the original free body diagram into a individual free body diagram for members A, B here and B, C down here. As I said, what I've been able to do is basically sum the components of the reaction forces at A into this singular axial force or tension AB from either direction acting on the member BC, acting on the member AB, right? So this is a complete free body diagram of the member AB. I have my coordinate system. I've included the angles as well at the for where the tensions are acting on the member. And also I've drawn a free body diagram of the member BC. So you'll recall from the solution method, for any members that are in contact, so here look, any 2 contacting members, we should have equal and opposite components. So that's why I've included my TAB here acting opposite to this TBA over here. See, equal and opposite forces acting at B. And then I've gone ahead and completed the free body diagram of member BC by including this externally applied force, the reactions at C, and any dimensions and angles that I'm given, right? So you'll notice now that the sub-free body diagram of member BC only has 3 unknowns, right? Because TAB is equal and opposite to TBA. So now actually, with this sub-free body diagram of member BC, I'm in a position now where I can apply the equilibrium equations in 2 dimensions to solve for these 3 unknown reactions, which is what I ultimately want to find in the problem statement, right? So what I do is I just go straight ahead and apply the equilibrium equations in two dimensions, right? I sum the forces in X. I'll have a positive component of TAB plus FCX. In the Y direction, I will have a positive component of TAB negative the externally applied force of 2000 newtons plus FCY, right? So that's where this equation comes from. And what I've done here is I've chosen to sum moments about B so that I don't have to deal with the sine and cosine components of TAB. I just say that I have a moment due to this force, which is going to give me a clockwise moment. So that's going to be negative at a distance of 2 meters. And then FCY is going to give me an anti-clockwise or counterclockwise moment about B at a distance of 4 meters, right? So the sum of the moments is only going to have 2 components to it. So I have 3 equations, 3 unknowns, and therefore I'm able to solve this system for the unknown reactions, and I should get the following. So please make sure that you can get these unknown reaction forces out of this system. So that's just a quick example of a frames problem. What I would also recommend that you do is review the example 6.6 on page 290. So make sure that you're comfortable with the outline solution in the textbook for this particular problem. You'll see that what happens in this case, which is different to the example that we've just looked at, is that because you have a fixed support here at A, when you draw the sub-free body diagrams of the individual members of this frame, is that you end up with essentially 5 unknowns for member AB, right? So we have the 3 reaction forces and the couple here that corresponds to the fixed support, and then these 2 equal and opposite forces acting at B. So we have 5 unknowns in this sub-free body diagram and 3 unknowns in this sub-free body diagram, right? So in order to get the reactions at A, we actually need to solve this one first and then move or translate these 2 unknown reaction forces, once we've found them, into this free body diagram to solve for these ones, right? So it's a little bit more involved, that example, but the technique is the same, right? So just make sure that you follow the solution method as we did in the previous example, and follow the notes in the solution set out in the textbook, and let me know if you have any trouble getting to these solutions down here. So the final thing that we're going to have a look at in this video is an example of a machine. Now, another swig of Gatorade. This is an example from the text, but also it's example 6.98 from page 300 in the textbook. So this one here. Let me find my pen to point with. So this is an example of a machine because it's a frame, right? Because we have this externally applied force acting some distance along a member, so we know it's a frame and not a truss, and it's also designed to move, right? So in the case of these pliers, it's designed so that the user can push the two handles in to exert a force on whatever's between the plier ends down here at point B, right? So it's a machine, and the question says that a woman exerts 200 newtons on the pliers as shown. It's 20 Newton forces onto the pliers as shown, right, with both sides of a grip. And we're asked to find the magnitude of the forces that the pliers exert on the ball bearing at B, and to also determine the magnitude of the force at C as well, right? And we're told that's a pin connection. So what I've done is I've drawn a free body diagram of the pliers. So I've got basically two members, although they're curved. I've drawn them basically with right angles and 45-degree angles, basically to make the math a little bit easier. So I've got this bottom member here, this top member here. I've drawn on my dimensions. I've drawn them in meters. I've converted them from millimeters to meters, and I've drawn on these two externally applied 20 Newton forces. So that's step one of the solution method, right? Draw a free body diagram of the entire structure. I now need to go ahead and identify all two force members. Now there are only two members for this machine problem, and they both have forces applied some distance along them. So they are loaded not necessarily at the joints, right? Which means that we have no two force members in this problem. Okay. So the next step is to disassemble the structure and draw a free body diagram of each member. So for the two members that we have, I've drawn a free body diagram of the top member and a free body diagram of the lower member. So how have I done that? Well, I've taken equal and opposite forces at C, right, because that's where the two members are in contact. So remember from the solution method I said we represent forces at any two contacting members with equal and opposite components in the X and Y directions. So point C is where the two members are contacting, which is why we have these equal and opposite reactions at point C. So for the top member, I've decided to draw them in the positive directions, and therefore for the bottom member I have them in the negative directions, but equally validly I could have drawn them the other way around, just as long as they're equal and opposite, right? And I also have this force acting on the ball bearing at B, and again I've drawn them equal and opposite in both members. So what we see here, like the first example that we discussed, is that we only have three unknowns now, so we're only required really to solve or apply the equilibrium equations to one of these two members. because I can apply 3 equilibrium equations to solve for these 3 unknowns. So that's exactly what I've gone and done down here for the top member. You'll see when I sum forces in the x direction, I have Fcx, and then I have a negative component of this 20 Newton force here. In the y direction, I have Fcy and a negative component of this 20 Newton force, and also Fby. That's where these 3 components come from. And I've chosen to sum moments about C to eliminate these 2 reaction forces. So I'll have a moment due to Fby, and I'll have a moment due to both components of this 20 Newton force, which is where these 3 components come from. So again, I have a system of 3 equations, 3 unknowns, and I should be able to solve for these values down here. So again, please make sure you can follow that solution method through and get the same answers that I did down here. Any questions on any of this stuff, please email me. If you'd like to discuss this via Skype, then I'm making appointments for people to talk to me. Just give me a day or 2 to arrange that. And if you think the question that you have is going to be relevant to everyone else in class, then please try to make use of the discussion tab on Canvas as much as possible, so that everyone can see my response to your question. But basically what we've done now is completed chapter 6, and we will move on in the coming days to chapter 7, which is all about centroids and centers of mass. So I hope you kept up with that. Again, sorry for my dodgy camera work. I'm trying to record these videos on my phone at home, yeah, any comments and suggestions are welcome. So cheers, have a good day.